Hello, my dear students. Please subscribe our YouTube channel for more free video lectures and click on bell button for notifications and visit our website to purchase full course.
Welcome back to another session of Strength of Materials. In previous session, we derived a formula for normal stress, shearing stress, resultant stress, angle of obliquity. So in this session, we are going to do some problems using all those formulae, right? So you may look into classroom workbook, chapter number 2, problem number 1, okay? Chapter number 2, problem number 1. So in this problem, state of stress is given. The state of stress about a point is given below. So sigma is equal to 5 minus 1 and 3. 5 minus 1 and 3 MPa. So state of stress is given. And we have to find normal and shearing stresses on 30 degrees plane, 120 degrees plane, lateral 45 degrees plane, and 135 degrees plane. Even we have to find resultant stress on these planes and the angle of obliquity on these planes, right? So we have to do this problem. So first, try to identify what is 5, what is minus 1, what is minus 1, what is 3. It is a tensor matrix of stress. In previous sessions, we discussed various aspects of tensor matrix of stress and tensor matrix of strain. The given matrix is tensor matrix of stress, and we can easily say sigma x is equal to 5, sigma y is equal to 3, and tau xy is equal to minus 1. All are measured in MPa. You may refer tensor matrices of 2D problems. If you refer two-dimensional problems, the shape of tensor matrix will be something like this. Okay. So first let us try to find various parameters on 30 degrees plane. Let us try to find various parameters on 30 degrees plane. Okay. First, normal stress. Normal stress on any plane is given by sigma x plus sigma y by 2. Right. Refer that formula, man. Here sigma x is 5 plus 3 by 2 plus sigma x minus sigma y by 2 into cos 2 theta, 5 minus 3 by 2 into cos 2 theta. If theta is 30 degrees, 2 theta will be 60. So here I have to write cos 60. Cos 60 plus tau xy sin 2 theta. What is tau xy? Minus 1 into sin 60, right? So we have used normal stress formula. In previous session we derived this. Now we are using this. If you simplify this, you get answer like this. The normal stress on 30 degrees plane is coming around 3.63. 3.63 MPa. 3.63 MPa, right? Similarly, shearing stress on 30 degrees plane, this is nothing but minus of sigma x minus sigma y by 2. So 5 minus 3 by 2 into sin 2 theta. Sin 2 theta means sin 60. So directly I am writing, man, right? Directly I am writing 60 here, right? Sin 60 plus tau xy cos 60. Tau xy is minus 1 cos 60. So this is coming around, the shearing stress on 30 degrees plane is coming around minus 1.36 MPa. Okay. So these two are for 30 degrees plane. Let us move on to, resultant stress. Resultant stress on any plane is square root of sigma n square plus tau n square. Here sigma n is 3.63 square plus minus 1.36 square under root, right? If you simplify this, you will get something like this: 3.87 MPa. And we know tan pi is equal to tau n by sigma n. From this, pi is equal to tan inverse tau n by sigma n. So here tan inverse, what is tau n? Tau n is minus 1.36 by what is sigma n? Sigma n is 3.63. So it is coming around minus 20.53 degrees. Minus 20.53 degrees. So we found normal stress, shearing stress, resultant stress and angle of obliquity for 30 degrees plane. You may copy all these things. You might have copied all these things, right? So we just did the first part of the problem. We found various stresses on 30 degrees plane. Let us move on, man, right? Now let us try to find various stresses on 120 degrees plane. Now 120 degrees plane. 120 degrees plane. Let us try to find various stresses on 120 degrees plane. Okay. So if theta is 120 degrees, 2 theta will be 240 degrees. Just I have to change this angle. Now this angle becomes 240 degrees. This angle also becomes 240 degrees. And this is coming around. This is 4.36, right? This is 4.36 MPa, right? Similarly, shear stress on 120 degrees plane. Shear stress on 120 degrees plane. Here I have to make this angle 240. If theta is 120, 2 theta is 240, right? So here also 240, and the answer will be plus 1.36 MPa. Plus 1.36 MPa, right? Now resultant stress. So here I have to make some changes. Resultant stress is equal to 4.36 square plus 1.36 square. It is coming around. So currently we are finding various values for 120 degrees plane. It is coming around 4.56. 4.56 MPa. 4.56 MPa. Then tan pi is equal to tau n by sigma n, and pi is equal to tan inverse tau n by sigma n. That means tan inverse plus 1.36 by, so here I have to make a correction here, that is 4.36. Now the angle of obliquity comes out as, the angular obliquity is 17.32 degrees. 17.32 degrees. Like this, we can find various values on 120 degrees plane. So please copy these four. I hope you copied. So we found various values on 30 degrees plane and 120 degrees plane. So here we see two things. Normal stress on 30 degrees plane plus normal stress on 120 degrees plane is equal to, what is normal stress on 30 degrees plane? 3.63. So 3.63 plus normal stress on 120 degrees plane, it is 4.37. It is coming around 8 MPa. Similarly, sigma x plus sigma y is equal to, sigma x is 5, sigma y is 3, 5 plus 3, 8 MPa. Please copy. Copy these values. Normal stress on 30 degrees plane plus normal stress on 120 degrees plane is 8, and sigma x plus sigma y is also 8. So normal stress on 30 degrees plane plus 120 degrees plane is 8 MPa, and sigma x plus sigma y is also 8 MPa. What is our understanding here? What is angle between 30 degrees plane and 120 degrees plane? Angle between 30 degrees plane, 120 degrees plane is 90 degrees. Indirectly, 30 degrees plane and 120 degrees plane are mutually perpendicular. Or normal stress on 30 degrees plane and normal stress on 120 degrees plane, these two stresses are mutually perpendicular normal stresses. Mutually perpendicular normal stresses. Similarly, sigma x and sigma y are also mutually perpendicular normal stresses. Sigma x, sigma y are mutually perpendicular. Sigma 30 degrees, sigma 120 degrees. These are also mutually perpendicular. So what is our conclusion? Write down this important point. Sum of any two mutually perpendicular, SUM sum. Sum means addition. Sum of any two mutually perpendicular normal stresses. Sum of any two mutually perpendicular normal stresses is constant, which is always equal to sigma x plus sigma y. which is always equal to sigma x plus sigma y. This is for 2D problems. In 3D problems, I may give a statement like this. Sum of any three mutually perpendicular normal stresses is always equal to sigma x plus sigma y plus sigma z. Sum of any three mutually perpendicular normal stresses is constant, which is always equal to sigma x plus sigma y plus sigma z. In 2D, only two stresses, man, right? Understand? Sum of any two mutually perpendicular normal stresses is always equal to sigma x plus sigma y. So this conclusion we are making here. Another observation, the shearing stress on 30 degrees plane is minus 1.36 MPa and the shear stress on 120 degrees plane is plus 1.36 MPa. So shear stress on 30 degrees plane, shear stress on 120 degrees plane is same, 1.36, 1.36. Very long back, some 10 sessions back, while dealing shearing stresses, I told mutually perpendicular planes carry same shear. The angle between 30 degrees plane and 120 degrees plane is 90. They are mutually perpendicular planes. Those planes are supposed to carry same shear. Here 30 degrees plane carries 1.36. 120 degrees plane also carries 1.36. They are carrying same shear. Not only this problem, man. In every problem, mutually perpendicular planes always carry same shear. Any problem because of complementary nature of shear. Okay? Right. Let's move to second part of the problem. For 30 degrees and 120 degrees we found. Now we are going to see another two planes. 45 degrees plane. 45 degrees plane. We entered second part of the problem. In the second part we have to find various values on 45 degrees plane and 135 degrees plane. Okay, so here I have to write, if theta is 45, 2 theta is 90. 2 theta is 90. Here also 90, right? So here also 90 degrees. Here also 90 degrees. And normal stress on 45 degrees plane is around 3 MPa. 3 MPa, right? Similarly, shearing stress on 45 degrees plane is minus 1 MPa. Minus 1 MPa. So normal stress is 3 MPa. Shearing stress is minus 1 MPa. Now I have to make something here. So the resultant stress on 45 degrees plane is square root of 3 square plus minus 1 square. That means how much? The resultant stress is coming around. So resultant stress is 5 MPa. Let me check it whether it is 5 MPa or not. So normal stress is 3 MPa, shearing stress is 1 MPa. It means square root of 9 plus 1, square root of 10. So you may do this. What is square root of 10? And similarly, angle of obliquity. So angle of obliquity can be found like this. Tan inverse minus 1 by 3. It comes around. The angle of obliquity is coming around. So here I didn't do it. So you may try to do it. So tan inverse minus 1 by 3, how much, right? Okay. Please copy these values, man, right? You may try to find what is square root of 10. And you may tell me what is tan inverse minus 1 by 3. This is coming around 3.16 MPa. 3.16 MPa. You may find angle of obliquity, right? Everything I wrote, simply just you have to put tan numbers in our calculator, you will get answer, right? You will get answer. So this is for 45 degrees plane. I hope you copied this 45 degrees plane. Alright. Now let us move to 135 degrees plane. Let us move to 135 degrees plane. 135 degrees plane. Degrees plane. If theta is 135, 2 theta should be 270. Here also 270. And here also 270. So here also I have to put 270. This is coming around 5 MPa and this is coming around 1 MPa. You may find resultant stress like this. Resultant stress is square root of 5 square plus 1 square, that means square root of 26. And angle of obliquity 1 by 5. So you may copy these values. These are valid for 135 degrees plane. 135 degrees plane. Right? Please copy. This is 5.09, 5.09 MPa. Okay. So please copy these values. These are valid for 135 degrees plane. 135 degrees plane. I hope you copied. Now you tell me sigma 45 degrees plus sigma 135 degrees equal to how much? 3 plus 5. That means 8 MPa. What is sigma x plus sigma y? Again it is 8 MPa. So what is your understanding? What is angle between these two stresses? 45 degrees, 135 degrees. That means they are mutually perpendicular. Angle between these two stresses is 90 degrees. They are mutually perpendicular. So again we have proved here. Sum of any two mutually perpendicular normal stresses is always equal to sigma x plus sigma y. Normal stress on 45 degrees plane plus normal stress on 135 degrees plane is 8 MPa. Sigma x plus sigma y is also 8 MPa. Again we proved mutually perpendicular planes carry same shear. 45 degrees plane is carrying shear of minus 1 MPa. 135 degrees plane is carrying plus 1 MPa. Numerical value is unchanging. So value of shear on mutually perpendicular planes is always same. So again we proved. Okay. So a problem could be given like this. And sometimes they may ask like this. What is sigma 10 degrees plus sigma 100 degrees? What is sigma 10 degrees plus sigma 100 degrees? Should you find sigma 10 and sigma 100? What is angle between these two stresses? 90 degrees. They are mutually perpendicular normal stresses. Their sum should be equal to sigma x plus sigma y. That means 8 MPa. You need not do anything. Directly you can say their sum is 10 MPa. Similarly, maybe sigma 70 degrees plus sigma 160 degrees is how much? What is angle between these two stresses? 90 degrees. They are mutually perpendicular. Their sum also should be equal to sigma x plus sigma y. You need not find what is sigma 70, what is sigma 160. Their sum should be equal to sigma x plus sigma y. So don't forget it, man, right? Sum of mutually perpendicular normal stresses is always constant, which is always equal to sigma x plus sigma y. And second point, mutually perpendicular planes carry same shear. So these 2 points you always remember, right? Let us move to another numerical, right? For our reference, you may copy, right? You may copy this. Let us move to another problem. Let us move to another problem. You may look into classroom workbook, problem number 2. You may look into classroom workbook, problem number 2. Okay, I hope you copied these two. Like this, man, sum of any two mutually perpendicular normal stresses is equal to sigma x plus sigma y. Okay, right. In second numerical, a plate is given. A plate is given like this, and it is carrying state of stress like this. This is 5 MPa. This is also 5 MPa. And this is 3 MPa. And this is again 3 MPa. This plate is also carrying a shear of 1 MPa. It is carrying a shearing stress of 1 MPa, like this. Here they have mentioned two planes. Two planes. One plane is like this, plane AB, and this angle is 30 degrees. Another plane is plane CD, and this angle is 45 degrees. So this is the given problem, man, right? In this given problem, we have to find normal and shearing stresses. Normal and shearing stresses on plane AB and plane CD. We have to find normal and shearing stresses on plane AB and plane CD. So let us do it. First, plane AB. Plane AB. Plane AB. What is angle made by plane AB? So try to recall, man. Always we have to measure angle with respect to vertical plane in anti-clockwise direction. This is theta, man. If this angle is 30 degrees, this angle obviously becomes 60 degrees. So for plane AB, theta will be 60. Always measure angle with respect to vertical plane in anti-clockwise direction. Always it is the case. Now what is sigma x? Sigma x is 5 MPa. What is sigma y? Minus 3 MPa. Why minus? Since it is compressive stress, we have to take minus 3 MPa. What is tau xy? It is minus 1 MPa. Why it is minus 1? In my derivation, on top face I have taken shear towards right. Refer my derivation. In previous session, we derived formula for sigma n and tau n. Refer the derivation. At the beginning of derivation, I took one plate like this. On top face, I applied tau xy towards right. So in this problem, the shear is opposite of that shear. On top face, if shear is acting towards right, you may take positive moment, right? If it acts towards left, you have to take negative. So that is why -1 MPa. Now you can easily find what is normal stress, what is shearing stress on this plane AB. So normal stress is equal to, we know this formula, man, sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta plus tau xy sin 2 theta. This is the formula to find normal stress. This is equal to, what is sigma x? 5. What is sigma y? 3. 5 minus 3 by 2 plus 5 minus into minus plus by 2 cos 120 plus minus 1 into sin 120. If angle theta is 60, 2 theta will be 120. So if you simplify this, sigma n is coming around minus 1.86. Minus 1.86 MPa. So this is normal stress on plane AB. Similarly, let us try to find shearing stress on plane AB. The formula is minus of sigma x minus sigma y by 2. That means minus into minus plus. So 5 plus 3 by 2 sin 120 plus minus 1 into cos 120. If you simplify this, the shearing stress on this plane AB is coming around minus 2.96. Minus 2.96 MPa. Please copy, man. For plane AB, these are the values. I hope you copied. Now let us try to find various parameters for plane CD. Plane CD. Plane CD. What is angle made by this plane? Always you have to measure angle of plane with respect to vertical plane in anti-clockwise direction. So let us try to find angle made by plane CD. So draw one vertical plane like this and measure angle with respect to vertical plane like this in anti-clockwise direction. Always measure angle with respect to vertical plane in anti-clockwise direction. What is this total angle? 135 degrees. So for plane CD, theta is equal to 135 degrees. Theta is equal to 135 degrees. Then you can easily find what is normal stress, what is shearing stress. So here, if theta is 135, the 2 theta will be 270. 2 theta will be 270 here. Here also 2 theta will be 270. So here also it is 270. Here also it is 270. The result will come like this. The normal stress on 135 degrees plane or plane series, it is coming around 2 MPa, right? So this is 2 MPa and tau n. So tau n will be, this is 4 MPa. This is 4 MPa. Please copy. So in this problem, two things we have to notify. One, always measure angle with respect to vertical plane in anti-clockwise direction. And second, if shear is acting towards right on top face, it is positive. If it is acting towards left, it is negative, like the ratio. So this is our second numerical. Second numerical, right? So let us do third numerical. You may look into classroom workbook, problem number 3. Classroom workbook, problem number 3. Okay. So in this problem, a shaft is given. A shaft is given. The shaft is carrying a bending moment of 5 kilonewton meters and a twisting moment of 10 kilonewton meters. And the diameter of shaft is 100 millimeters. So diameter of shaft is 100 millimeters. A shaft of diameter 100 millimeters is carrying a bending moment of 5, twisting moment of 10 as shown. So here we have to find what is normal stress, what is shearing stress, what is resultant stress, and what is angle of obliquity on 30 degrees plane. So they have taken a plane like this, right? This plane is making an angle of 30 degrees plane. 30 degrees plane. Let us do it. Let us try to find all these values about this point, about a point on surface of this shaft. From point to point, stresses may vary. We try to find all the parameters about this point. Okay, right. So because of bending moment, bending stress will induce, and maximum bending stress is given by M by Z. In beams we learn all these things. Maximum bending stress is equal to M by Z, and here M by section modulus is pi by 32 into d cube. That means 32 M by pi d cube. So this much of maximum bending stress may induce in this shaft. Because of twisting moment, torsional shear stress will induce. The maximum torsional shear stress is given by T by J bar. Here T means twisting moment, J bar means polar modulus. So this is equal to T by polar modulus of cylindrical shaft is pi by 16 into d cube. If I simplify this, I get 16 T by pi d cube. 16 T by pi d cube. So the shaft is carrying two loads, two stresses will induce. So let us try to find what is maximum bending stress, right? The maximum bending stress is coming around, this is 50.92 MPa, and maximum torsional shear stress is coming out as 50.92 again, 50.92 MPa. Okay. So here we are going to find various parameters about a point on surface, man. Bending stress is always maximum on surface. Even torsional shear stress is also maximum on surface. Neutral layer doesn't carry any bending stress, and neutral points will not carry any torsional shear. So both bending stress and torsional shear stresses would be maximum on surface. This point is lying on surface. Okay. Now one more point. Always bending stress may act parallel to length of the lamina. In beams, we will understand, man. While deriving bending equation, we will understand everything, right? Okay, what we understand? Bending stress always acts parallel to length of the lamina. That is why it is also called as longitudinal stress. Longitudinal stress. Okay, so I assume bending stress as sigma x. It is 50.92 MPa. I assume torsional shear stress as tau xy. It will come around 50.92 MPa. If you know, if this is x-axis, if this is assumed as x-axis, and if this is assumed as y-axis, definitely my notations are same. My notations are valid, man, right? So stress parallel to x-axis, bending stress, stress about xy plane is 50.92 MPa. Now what is sigma y in this problem? Sigma y is 0. So in this problem, for that point, sigma x is 50.92 MPa, tau xy is 50.92 MPa, sigma y is 0. So now we have to find what is sigma n, what is tau n, etc., etc. Now we can easily find. First copy these two terms. I hope you copied. Now we can easily find what is normal stress, shearing stress, resultant stress, angle of obliquity, all these things very easily. So normal stress sigma n is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta plus tau xy sin 2 theta. So here what is sigma x? 50.92. 50.92 plus 0 by 2 plus 50.92 minus 0 by 2 into cos 60. If theta is 30, 2 theta should be 60 plus tau xy again 50.92 sin 60. If you simplify this, the normal stress on 30 degrees plane is coming around, this is coming around how much? Okay. 82.28. 82.28 MPa. 82.28 MPa. Similarly, we can find shearing stress, man, right? We can find shearing stress, tau n. So tau n is equal to minus of sigma x minus sigma y by 2 into sin 2 theta plus tau xy cos 2 theta. So this would be around, what is sigma x? 50.92. 50.92 minus 0 by 2 into sin 60 plus what is tau xy? Tau xy is also 50.92. 50.92 into cos 60. If you simplify this, the answer will be around 3.41 MPa. 3.41 MPa. Similarly, you can find resultant stress. Resultant stress is equal to square root of sigma n square plus tau n square. It will be around 82.35. 82.35 MPa. Even you can find angle of obliquity. Angle of obliquity comes around 2.37 degrees. Okay, 3.37 degrees. Please copy all these values, right? For problem number 3. Let us do one more problem before ending this session. You may look at classroom workbook, problem number 4. Problem number 4. So in this problem number 4, a bar is given. A uniform cylindrical bar is given. A uniform cylindrical bar is given, and this bar is carrying an axial compressive load of 10 kilonewtons like this. 10 kilonewtons. And the area of cross section, okay, diameter of bar is 100 millimeters. So we have to find various values on 45 degrees plane. 45 degrees plane. So please copy this. Okay. So in this problem, stress is not given, load is given. So what load? Compressive load. Because of compressive load, compressive stress will induce. Right? So before that, just I align x-axis parallel to length of this bar man, right? X-axis is parallel to length of the bar, and obviously this will be y-axis. Okay? Right. Then what is normal stress along x-axis? This is nothing but minus 10 into 10 cube by pi by 4 d square. What is d? 100 square. Why I am putting minus? Since it is compressive load, I am putting minus. Why this 10 power 3? Since it is in 10 kilonewtons, just we are converting this into newtons, man. Okay? So how much it is? If you calculate this, the sigma x will come out as 1.27. 1.27 Newton per millimeter square. What is sigma y? Any stress is acting parallel to y-axis. No stress. Any shear here? No shear. About xy plane, about x plane or y plane, no shear is acting. On x plane it is not acting. On y plane also it is not acting. So tau xy is 0. Now we can find what is normal stress. Normal stress sigma n is equal to sigma x plus sigma y by 2. Here sigma x is 1.27, sigma y is 0 by 2 plus sigma x minus sigma y by 2 into cos 2 theta. If theta is 45, 2 theta is 90 plus tau xy sin 90. So how much it is, man, right? It is, of course, here minus I have to put, right? Because it is compressive stress. It is compressive stress, I have to put minus. So sigma n is about minus 0.635 Newton per millimeter square. Minus 0.635 Newton per millimeter square. Now let us try to find tau n. So tau n is equal to minus of sigma x minus sigma y by 2 sin 2 theta plus tau xy cos 2 theta. Cos 2 theta. This will come around 0.63 MPa. 0.63 MPa. Okay, so these are the result, man. And if you want to find resultant stress, even you can find resultant stress. So number 3, resultant stress sigma r is equal to square root of sigma n square plus tau n square. We know what is sigma n, we know what is tau n. If you simplify this, you will get 0.89 MPa, and angle of obliquity is tan inverse tau n by sigma n. If you simplify this, the angle of obliquity comes around minus 45 degrees. Minus 45 degrees. So on this inclined plane, a normal stress of how much is acting? 0.635 MPa. And what is shear? Shear is 0.63 MPa. Shear acts like this, 0.63 MPa. So on this 45 degrees plane, a normal stress of 0.635 MPa is acting. A shearing stress of 0.63 MPa is acting. So like this we have to do. Okay. So you may copy all these things. So first you may copy these two. Sigma n is equal to minus 0.635. Then tau n is equal to 0.63 MPa. Please copy these two. Then you may copy these values. This is end of this session. Until meeting in next session, have a nice day. Thank you very much.